Okay, so now we're into the part where we're looking at the details of the software and how we get to use the timers. And you can see there's a couple of things that make this pretty similar to devices on the microcontroller that we've had to use before. We have to obviously enable the timer output, and that's with the main output enable here. And then we have also the OSSI bit, which is the off state selection for idle mode. We have the OSSR bit, which is the off state selection for run mode. So that's this one, and the OSSI was here. And then finally, we have the CCXE and the CCXNE. So these are the the enable of the capture and compare output or complementary output. The N stands for the negated output. And it talks a little bit about that within this table right here. And so clearly you can see the output compare output state for the normal state, as well as the negated state. So anyways, you can see here ways that you can disable or enable certain outputs. Like, for example, this one with the CCXNE bit not on, you can see that the output is disabled for the negated output state. So here you can see when both bits are on, you can get both the regular output state and then the complementary output state. So notice it says OCREF and the complementary to OCREF. One thing that I think is sort of confusing is some of the things you look at right here, is it's telling you, okay, what happens with certain things, or you have that polarity bit that we talked about. And remember, what does the polarity bit do? If you look at OCREF and then you look at the polarity bit can just basically switch the way the output would be. And that's what it's trying to show here. I don't think it looks the greatest, because this says OCREF, looks like it's saying OCREF ORed with polarity is what that OCXN output state would be. But I think it says it more carefully here. It's the negated state, or the complementary state, is equal to OCREF exclusive ORed with that polarity bit. And that means, the exclusive OR, remember, when you're doing exclusive OR, it's basically you're exclusive ORing with 0 and you get the same signal out, or you exclusive ORing with 1 and it's going to toggle it. So I don't think it's really hard to figure out, what way one is or the other. But remember, there's two different ways you can do that. You can either do that with the mode bit, basically, for PWM mode 1 or 2, or you can also negate it with the different regular output or the negated or complementary output. So it can be a little bit confusing there. And it shows here the same thing. Here's that OCREF exclusive ORed with the polarity bit, and notice it's different here. This is the NP bit for the negated timer or complementary timer. So they have these polarity bits that you have to look at for that as well. Anyways, it's not really anything that you have to be super careful about, but just be aware that you have to enable the timer, you have to enable the capture and compare output that you're doing, and then you have to make sure you're aware of the polarity bit that you're doing. And if you're getting the opposite of what you just expect, just flip it. Okay, so anyways, that's basically what's going on here, and you can see, well, if you don't enable it, then the output is disabled or you're in the off state. So it's not really that big of a deal for either one of those. Okay, so now let's talk about what we want to do when we're doing input capture. Now, input capture is different than the output compare, because what you're trying to do with the input capture is generally you're trying to monitor what frequency comes in or when you have some start or stop event that can be monitored by rising or falling edges or both. And so this one's trying to show what would happen if your external signal is in either red or blue and you're rising both the you're monitoring both the rising and the falling edge. So it'll clock this time here and clock this time here for the red signal as well as it would for the blue signal. And you can use those times to get you the period of that or whatnot. You could also use this alternatively to use a monitor for only rising or only falling edges. An external signal 3, the red one, shows what happens if you're only monitoring rising edges. And then by the same token, if you were monitoring only falling edges, you get this time here for the blue one. So you have to be aware which type you're doing. And as I say, you have the ability to monitor rising, monitor falling, or monitoring both edges. Okay, so how that's done, you can see we have some edge signal, external signal that's applied to the edge detector. That's the signal that we talked about in red and blue there for the previous two slides. And then you have the clock signal that's coming into the timer. So the timer is counting, the free running counter is just going and going and going. And whenever that external signal detects an edge, whichever way you tell it to start detecting edges, it's going to say, oh, let's look and get the timer counter when that edge occurred, and I'm going to capture that value. And either it can generate an input, or we just find some way to note that, okay, it captured a value and we have to do something with it. Okay, now there can be a couple of problems when you do this, and the main one we're going to talk about here is what happens if our external signal looks terrible like this. You might say, why would it look like that? Well, if you, let's say you hit a button, and this button, when you hit it, it's basically providing a connection where it's shorting something to ground. But when you hit the button, it may not fully seat on the connections, so it may lift up a little bit and so forth. So you get sort of this bounce that can occur right here. So you could have input filtering with our input capture that basically says, okay, if we're monitoring for a falling transition, we have to wait for more than one consecutive transition, or one consecutive clock cycle where the transition has occurred. And we can do more filtering than just that. We could say 2 or 4 or whatever. But you can clearly see, okay, it's supposed to have gone down there to the minimum, and we should, if everything was perfect and we had no bounce, maybe we'd have something like this for our signal, and then maybe this one would indeed trigger it. But since it's going up and down, that one doesn't count. And so here is the first one where there's no strange transition, and then here's the second one. And so this would be the reading that it would get from whatever the timer count is right there. And so now notice the sampling clock is basically showing that it's the timer clock, and it's slower than, it's going to be some multiple of the period, so that it can, actually detect the transition with some sort of filtering mechanism. And you can do it, as I say, no filtering, you can do some filtering, you can increase the filtering even more, and so forth. Okay, so here's sort of the overall input capture diagram here. And let's see what's happening in this particular situation, because we get to see quite a few of the overall bits that we need to be aware of for this particular input capture setup. Okay, so first off, we have this external signal that is coming into our input capture. We have this filter down converter, that's what we talked about there, and it's in this capture control master register, and there's 4 bits that will basically tell you, which has obviously up to 15 possibilities for this filter duration that you have there. Then this edge detector is basically what is going to look at the the rising edges, the falling edges, or both rising and falling edges, so that's there. We have this prescaler that's doing the same thing, and notice some of these are in the same registers that we had before. And the prescaler is doing the same thing about determining are we going with the actual clock frequency for the timers, or are we going to try to slow it down? So nothing's different there. And then we can see when we have that, when we have this going through the prescaler, then we have a couple of things that we need. We need to get some sort of setup that says, hey, we triggered on a particular rising edge or falling edge or both, and we need to capture that value. So the counter is going to, whenever this happens, it's going to signal the trigger to the counter, which will take and capture the actual counter value in the capture and compare register. And we have a couple of things that we can do. If we're doing direct memory access and that's enabled, we can use this and go that way. But if we haven't really talked about that, otherwise we can use, if the interrupt enable is enabled for capture and compare, the interrupt flag will be set, and we can go and do an interrupt request. Now, if it's not doing that, we can just look at the status register. Notice it holds the interrupt flags and the overcapture flag. We can just look at that. We can look at the status register to give us information about what has happened with the capture. Now, obviously, if we're trying to use this information, we may need to store that data that's in the status register and the capture and control register to give us, period length or frequency or whatnot. Okay, so as I said, what are the important registers? What bits are we going to enable, and what flags are we going to use when we do this? So in general, here's what shows so much of the different diagrams of the block diagram of just the timer in general. You see lots of different things within this. Here's the timer channels for a particular timer. So there's 4 channels, which again, that should make sense because we have 4 capture and compare registers, and you see that they all look sort of similar here with the edge detectors and the filters and so forth. So here's the capture and control registers that can capture the data or provide us output compares if we're doing something with pulse width modulated signals, and so that gets outputted onto the timers if we go back to the output. This other stuff up here just has to do with triggering. You can see this external trigger for the timer and so forth. Here's the auto reload register, so the ARR stuff that we've talked about. Here's the prescalers that we've also talked about. So we've sort of looked at all of this in a little bit of smaller detail or finer detail as we've gone through these particular sections. Okay, so one of the things that we've got to do is we've got to see how we're attaching to the timers, especially if we're wanting to bring out a pulse width modulated signal onto an output, or we're trying to read something from an external pin into the timer. And you can see one section that we've talked about in previous setups is what are we going to do for these GPIO pins when we want to do an alternate function. And this is showing a number of different things. So notice, for example, here's port A0 through 15, and look, they're tied to some specific alternate functions. So alternate function 1, for example, could be timer. We could see that port PA0 is tied into timer 2 channel 1 if we choose to use alternate function 1 for that port. And then you can see consecutive spots. So timer 2 channel 1 through 4, there's 4 channels. Go for port A0 through port A3, and so forth. And alternate function 2 would be timer 5 channel 1 through 4. So we have to select the appropriate alternate function for the timer that we want to use, and then we have to realize what is going on. So what I mean by that is, if we had chosen alternate, we could obviously use timer 2 or timer 5, but if you're going to use timer 5 in your program, then you have to use alternate function 2 when you set it up. Okay, so here's looking at the motor registers and the alternate function register that we really haven't talked about at all here. So what is going on with this particular slide? Let's look at it. Okay, so this is doing something for particular port PA0, and let's see what it is indeed doing. Okay, here we've seen this bitwise ANDing, and we know that what's going on here is, okay, these last 2 bits are going to be 1, 1, the rest are going to be zeros. And so when we complement that, what are we doing? We're going to have 1s everywhere, and zeros are going to be in these 2 bits. So basically we're clearing out those last 2 bits in this motor register, right? So that's why we're dealing specifically with port A0. And then notice what it's saying. We're going to load 2 in there and left shift it 0 times, since this is PA0. So 2 is 1, 0. Well, the motor register, what is that doing when we put in 1, 0? We are saying, okay, we are using the alternate function mode for that port. So that's what's going on with just this segment here. So you're going to see this as a set of revised code for our templates that for the timing parts. Now what's this? This is looking at the GPIO registers, and it's looking at the alternate function register. And so Within the GPIO registers, there's the alternate function register, and you can also see this sometimes written as AFRL for the lower bits of that. And so let's see what we're doing here. Okay, this is the same kind of thing. We've got this and that. So for this, we have 1, 1, 1, 1 in that last 4 bits. So when we complement that and bitwise AND it, basically what we're doing is with those lower 4 bits, we've got zeros in there. And then it says, okay, what are we going to do? We're going to exclusive OR, not exclusive, yes, exclusive OR, excuse me, no, bitwise OR with 1 shifted 0 places. Okay, 1 shifted 0 places is going to put 0, 0, 0, 1 in there. It's not being shifted. So what does that mean? Well, from our previous slide, we're choosing PA0. If we choose 1, that means we're choosing alternate function 1. So that means the timer we will be using is timer 2, channel 1. So that's what will be hooked up to pin PA0 on our board. Okay, now what's the rest of this stuff here? This is more set up for the timers, and let's discuss what each one of these is doing. I said we'd talk about this in a little bit more detail. This sort of comes from your book, and one of the things that I think is a little bit crazy when you start to look at this is they have all of these sort of pseudonyms for just placing ones or zeros in certain bits, and it's really helpful if you look at the at the setup or startup constants file to see what's going on. So let's look at that and see if we can't find out what's going on here. Okay, so now we're going to start to look at some of these other statements here that we really haven't looked at the these registers before for the timers. And so let's see what happens for a couple of these statements, and especially let's do something a little bit different since before it was fairly obvious and we didn't have too many of these important things from the header file that needed to be understood. You'll start to see a lot of these in this section, and so let's try to understand what's going on here with these particular segments of code. Now, of course, I'm going to start in a weird location, and that is this line right here. Okay, we can see that we're putting in the CR1 register of timer 2 that we are doing something that looks like enabling. So let's just see what that is and go from there. Okay, so let's go look at the CR1 register. Here it is. CR1 is timer control register 1. Remember, we're doing timer 2 because we were attached to port A0 and we use the appropriate alternate function setup so that we can have timer 2. Okay, you can see the bit that we're looking at is likely this one right here, and it says, okay, if it's 0, the counter is disabled. If it's 1, we enable it. Okay, so likely we need to enable that, and that means setting it equal to 1. So let's go back and look at this particular setup right there. If we think about it, basically what we could have done here is we could have exclusive OR'd this with 0x00000001, because we're bitwise ORing it, so we could have just ORed it with that to enable it. But let's see what indeed that is in our header file, because that's an important concept. Okay, so I'm going to switch out to Drawboard PDF here, and when I do that, you'll see, what is it? I'm going to highlight it. You can see in your header files, they basically have separate sections for like the timer, for the A to D, for the D to A, and each little subsection you can find. So I've separated out, and you'll see it on Blackboard as well, the timer version. And so here is the particular one we're looking. Oops. It's not going to let me erase it. Well, you can see it shows this counter enable right there, and it's equal to 1, exactly as I suggested. Let's see, I need to switch colors. So what I'm talking about is right there. So it's 1. That's the definition of it. So basically, that is an easy way to remember it. And you can see what this is doing for all of these is it's basically giving a definition for a bunch of different situations, and then you can just remember the bit. Sometimes remembering the bit is not so intuitive, and it may just be easier to do it, just looking at the register itself than going back and trying to remember what it says. But to another user that's coming to look at the code, it is probably easier to do that, because you could guess that that's enabling the timer. But remember, if you didn't have this startup file here with these particular definitions, that wouldn't mean anything to the compiler. So it's basically, every time you put that, it's replacing that right there with this right here. And if you didn't have that in there in the header files, then it wouldn't know to do that. So make sure you're aware of that. And I guess I should point out one other thing. These definitions are based on what this book is using. You might remember there's another board that I've talked about. I think it's called the TI Launchpad, and it's similar to this, but its book has all sorts of different definitions. Of course, they're doing the same type of thing, but you can't use like the header file for this one with that. Well, maybe I shouldn't say you could use the header file, but you can't use that header file with all the codes that they would have in the books that go with that TI Launchpad, because the nomenclature is not the same. So be aware that that's going on. Okay, so now we've settled what's going on with this bit. And so we've put that right there, and this is enabling the timer. Okay, now what is this? We've got, you can see, 3 other registers that we've got to look at. So let's see what these are doing as we go through this. Okay, we have the CCMR1 register, so let's look there. Okay, this is for just the control register. This is the slave mode control register, the status register, the event generation register. Here we go, the capture compare mode register. Obviously that's something that we sort of were wanting to look at. Okay, so what's going on with this one? Well, and again, this comes from the huge manual for the STM Discovery Board, and it can be a little bit tough to see, but let's see. Again, we know what we're looking for here, and we know we are looking, in particular, it says TIM CCMR1 CC1S0. Okay, again, we don't really know what that means, but let's see what it means. We have to go to our setup here, and notice these are organized for the registers. So the first one is the CR1 register, CR2. We've got to get to the CCMR1, and it should be after the EGRs. Okay, so here we are. So this is right here. We have that. And you can see that basically this is CCMR1 underscore CC1S underscore 0 is setting bit 0 to a 1. CC1S underscore 1 is setting bit 1 to a 1. So let's go back and see what that is. Notice we are only setting bit 0 to a 1, and we're putting that in there. So let's see what that does if we do that. Okay, so it's these two bits here, and you can see, what does it show? It shows here, got to go over here because we're way back. We're looking at these bits. It says the bit field defines the direction of the channel, input or output, as well as the used input. Okay, we didn't do anything with bit 1, so assume that it's just left at 0. Okay, so what we have done with the 0, 1, so we've set this bit to 1 and we didn't do anything there, so we can assume that it is left at 0. It says compare capture 1 channel is configured as input. Input capture 1 is mapped on TI1. So that's what we're doing right here. Okay. So go back here. So we're basically doing input capture on TI1. And remember, this one is doing something interesting too. We have CC1P and CC1NP of the CCER register. So let's go back and look at what that is. Okay, here's the CCER register. Now notice, you can see these are got all these polarities, right? Well, we're doing this one. Oops, excuse me, not careful. We're doing CC1P and CC1NP. And you can see when we do this, this is the capture and compare right here. And right here. Now notice, what do you expect that they're actually doing in this? We have to go to our bit definitions. Oops, I'm going the right direction. Okay, so here's the CCR, and we have what? CC1, let's see, let's make sure we do it right. CC1P and CC1NP. And you can guess, you see they're ORed together, and so you're doing something with the complement and ANDing, so be aware that that's what you're doing. So CC1P is right here, and CC1NP is right there. Okay, and so we're setting, this is 2 and 8. So basically 2 is putting a 1 in bit 1, and 8 is putting a 1 in bit 3. So we're putting 1s in those, right? And so that's what this bit definition is. So we're basically putting in here a 1 there and a 1 there. So bit 1 and bit 3. But remember, specifically what we're doing here is going back to our code. We are doing, so we're putting a 1 and a 1 in for bit 1 and 3, but we're complementing that. So that means every other bit is a 1 and those bits are 0. So we're clearing out those bits in the CCER register. So what is that doing for us? Okay. It says CC1 channel configured as output. This is basically the output polarity, and what we see here is it shows a couple of things. It says CC1 channel configured as output, and it says CC1NP must be cleared in this case, and it says CC1 channel configured as input. This bit is used in conjunction with CC1P to define these timer polarities, and it says refer to the description there. Okay, and then it says CC1P is right there, and you can guess it says CC1 channel configured as input. Well, that's what we were doing here. We weren't configured as output, we were configured as input, because what we're trying to do is input capture. And it says, okay, well, if those two bits are 0, 0, then we're doing rising edge for our particular input capture. Obviously you can see 0, 1 is falling edge, and then 1, 1 is used for both edges. So right now what we've done with this statement is input capture rising edge. Okay, that makes sense here. Now, why are we not using this as some bit pattern? Obviously we could, but this is the slave mode control register, and we're putting in 7. What is 7? 7 is 1, 1, 1. So we're putting in 3 bits. We're not shifting it at all. So we're putting in 111, it's shifting at 0 bits, and let's see what that does to that register. Okay, clearly we're doing something with those 3 bits right there. And it says SMS slave mode selection, and it says, okay, that's right here. Okay. Well, what does it look like we did? We set it as this because they're all zeros. I mean, they're all ones, excuse me. And it says, rising edges of the selected trigger clock the counter. Oops. Forgot to. So, notice this is the slave mode selection. It says when external signals are selected, the active edge of the trigger signal is linked to the polarity selected on the external input. And so anyways, probably a little bit more complicated than it needs to be, but the point is rising edges of the selected trigger clock the counter. Okay. Here we're ORing this, bitwise ORing with the slave master control register TS0 and TS2, so you can bet those are 2 bits. And let's go and again verify that that's what we have going on here. We have slave master control registers up here closer to the top. TS0 and TS2. Yep, just as we expected. We're setting those bits. So notice that it says bit 0, bit 1, and bit 2, but that's because they're in a different location, right? They're in that second set of, within the slave mode control register, they're in the second set of 4 bits. So that would be bit 4, 5, 6, and 7. And so while it says bit 0 there, that's bit 0 for the TS. So let's go see what that is. Okay, so those are right here, and notice it's not doing anything with this bit, it's just we're setting bit 4 and bit 6. So bit 4 and bit 6, it says is going to be 1, 0, 1 there. So that's filtered timer input 1. So that means we're doing filtering in this particular setup. Not big one. Okay, so basically this is, the generic idea of what's going on here is when we come back over this, what we're doing is we have to set the motor register to set up port A0 in an alternate function mode, and it's coming into timer 2. And then we have to set up timer 2 And what we're doing for that is we're setting it up for input capture on the first one, on TI1. Then we have to do that, we're setting it up to capture rising edges. And then we set up that we're trying to do some sort of filtering timer input, so we could either skip, like we did in that one setup. We could skip if it isn't 2 consecutive rising edges or 3 consecutive rising edges. We didn't say what we set that up to, but that's what we did. And then finally we said after we're filtering it to enable the timer. So this is sort of the revised code that you're going to see for using port A0 as an input signal. And this is sort of in that template that you will have for this particular lab. And these are really complicated sometimes, and they're coming off of what Dr. Zhu uses in the book, but I think it's worthwhile trying to go and navigate and see what's going on with these bit patterns. So there we have it. That's all this one slide in a nutshell. So you can see here this timer capture compare mode register. We're trying to set the CC1S bits, which basically tell you whether you're using this in input capture or output compare mode. Okay, so these 2 bits, and we put in this, if you look at the bit patterns, 0, 1. I accidentally showed you what was going on through the output compare mode because I was looking at this, and all of this is talking about that, even though I sort of looked at this page over here. I wasn't really looking at it appropriately, although you see there it is, it's saying it's configured as input. I really should have been looking at the input capture mode, which shows right here, because that's what I was truly looking at. Now it's right before, because you have to have 0, 0 to be doing an output, but we are doing 0, 1, which is this particular one right there, and it says compare capture 1 channel is configured as input IC1, so input capture 1 is mapped on TI1. That's the same thing I said over here, but I was not looking at in the appropriate mode. I should have been looking at the input capture mode section. It's fine. Because again, what makes sense there is here's the filtering parts that I was talking about. Now we didn't change that, right? We didn't put anything there. So if we didn't put anything there, we told it to filter, but we didn't tell it to actually filter anything, because we let those bits be zeros there. If we change those, then we would have had that filtering actually taking place. Anyways, you can see what's going on there, and that's just finalizing this and showing it more carefully with that input capture for the capture compare mode register.